Hello everyone, it's me, Professor Aaron Albert, here again with Lesson 20. Let's learn some econ. So today we're going to talk about Pareto optimality, what it is, what it isn't, and kind of justify it as a minimum standard for good outcomes from an econ point of view. Additionally, we're going to start talking about Edgeworth boxes, and we're going to use them as our tool to think about Pareto optimal outcomes to economic problems like we've been looking at. And today we'll also figure out how in an Edgeworth box we can find the contract curve graphically. So the first thing we want to do is talk about what efficiency means in general. So suppose you have some initial allocation of goods. That is, you have certain groups of people. Let's say you have 10 people. Let's say you have fixed amounts of, say, 10 goods. We could then allocate each of these goods in some proportion to each of the individuals and create what I'll call an initial allocation, i.e. you're just dividing up the fixed amount of goods you have among the number of people who could have them. Now, imagine you have some initial allocation, and then suppose someone said that they could find a Pareto improvement. We will define a Pareto improvement as some other way to allocate the goods such that at least one person is better off than they were under our initial allocation, and no people are any worse off than they were under the initial allocation. Does that sound like something that we would want? My thoughts is yes, right? If we can make at least one person better off and not hurt somebody else, that seems like it would be a good thing to do. So we will say that some sort of allocation is quote-unquote Pareto efficient. This is the same as Pareto optimal, right? Pareto optimal, Pareto efficient, same thing. We'll say an allocation is Pareto optimal or Pareto efficient if there are no Pareto improvements possible. That is, you found an allocation and it's not possible to rearrange the goods to make somebody better off without hurting somebody else. I think once you have this firmly in your mind, it's relatively intuitive, but it's a slightly strange concept if you haven't encountered it before. The reason this is important is because it's a good starting point for if we're going to choose outcomes, right? If we have a bunch of people and a bunch of ways to divide up the resources, there's lots of ways we could do it. In fact, there's a large number of infinities of ways to do it. But we're saying, well, we should just look at the ones which we can't Pareto improve upon, i.e. the ones that we think are quote-unquote Pareto optimal. With this in mind, I will give the most succinct definition I know of for Pareto optimal, for Pareto efficient, and it is as thus. If an allocation is Pareto efficient, every resource is optimally allocated to serve each individual or entity in the best way while minimizing waste. That is, any changes made to assist one entity would harm another. That is, again, if your allocation is Pareto efficient, it is not possible to find some other allocation that makes at least one person better off without harming somebody else. Now, in order to think about Pareto optimality and Pareto improvements, let's do a little practice. Here's a silly situation in which you could encounter. Picture you come downstairs and you notice that your 3 children or siblings are fighting over an orange. And now their preferences for the orange change from individual to individual. We're going to assume that Mary wants the rind of the orange so that she can zest it to make a cake. This is sort of a story way of saying Mary has a utility function that is continuous and increasing in the quantity of orange zest she gets. Conversely, Katie wants the juice from the orange because she wants fruit juice. So she just wants the fruit, no zest. That is, Katie's utility is continuous increasing in the pulp, in the meat of the fruit. Brian just likes orange. He wants some orange. So again, if we wanted to be pedantic, the utility of Brian is continuous increasing in both the peel and the meat. He wants all orange. All orange is good to him. So my question is, here are 5 potential ways to divvy up the orange. Tell me if each is Pareto efficient. And if it's not Pareto efficient, you must tell me what a Pareto improvement might be. That is there some way to reallocate that orange among the 3 individuals such that at least one of the individuals is better off and nobody is worse off. The 5 allocations we'll consider initially are going to be 1, give Katie the whole orange. 2, give Mary the whole orange. 3, give Brian the whole orange. 4, give Mary and Katie each half of the orange. Just cut it in half. And then lastly, what if we give Brian half the orange and Mary half the orange? Take a few minutes, read through each of these solutions as well as the utility functions that I've given you, and if you need to, refresh yourself on the definition of Pareto optimal, and tell me if each of these is Pareto optimal allocations, and if not, how could I improve upon my allocations? Go! Alright, hopefully you've done the exercise. Assuming you have, welcome back. Hope it was fun. So let's look at these one by one. Suppose I give Katie the orange. Is there any way to reallocate that orange such that at least one person is better off and Katie is no worse off? Yes. Katie only values the fruit. So I could Pareto improve upon this by taking the fruit, giving it to Katie, then taking the peel and giving it to Mary. If I do that, I have made Mary better off and not hurt Katie. Therefore, the first listed one is not Pareto optimal. There are, for each of these that do have Pareto improvements available, infinite other solutions. All we have to do is find one. We find a single way to Pareto improve. It is not Pareto optimal. So let's try the next one. Is it Pareto optimal to give Mary the orange? If you want to revise your answer from originally, take this time to do it. All right, so if Mary has the whole orange, couldn't I take the fruit from Mary and give it to Katie? If I do that, Mary is no worse off because she didn't value the fruit. Katie is better off because she values the fruit and gets it. And Brian's no worse off because he still has nothing. So that would be, for sure, a Pareto improvement. Therefore, this also is not Pareto optimal. Moving right along, what do I give Brian the whole orange? I just hand him the orange and say, Katie, Mary, you don't get nothing. Is that Pareto optimal? Yes. So imagine Brian has a function that is continuous and increasing in volume of orange that he's got, because he's going to stuff it in his face. Any other allocation will make him worse off. So I could say, oh, Brian has the whole orange. Let's try giving Mary the zest of the orange and giving Brian the rest. Well, that makes Mary better, but Brian worse. Not a Pareto improvement. Okay. What if I give Katie the pulp and Brian the rind? Well, again, that makes Katie better, but Brian worse. So what if I just take the orange and throw it out? Well, then I've made everyone worse. There is no way to reallocate the orange such that anyone is better off without hurting Brian. So therefore, this one, Pareto optimal. Moving right along. Let's say I take the orange, cut it right in half, and I give half the orange to Katie, half the orange to Mary. Is that Pareto optimal? Hopefully at this point you're seeing a pattern. No. Mary has half of the fruit, and Katie has half of the fruit's zest, and each of them don't value that. So this is not Pareto optimal because we could just make each of Mary and Katie better off by having them trade fruit and peel so that they each have what they value. So that one's not Pareto optimal. How about I give Brian half the orange and Mary the other half the orange? You can just cut it right in half. Again, this one's not Pareto optimal because Mary has half of an orange worth of fruit she doesn't value, so that isn't Pareto optimal. Ways I could Pareto improve? Well, I could give Brian the entire orange and then Mary half the zest. That seemed to be a Pareto improvement because it makes Brian better off and doesn't hurt Mary. So now. All right, now we're moving on to more exotic splits. Try each of these. First, give Brian the fruit and give Katie the rind. Is that a good allocation? No, this one I was just being tricky. Katie gets the rind, Katie values the fruit. So that seems silly. We can Pareto improve by instead giving Brian the fruit and Mary the rind. That makes Mary better off, doesn't hurt Katie, doesn't hurt Brian. So that one's not Pareto optimal. Last one. Give half the orange to Brian. Give Katie half the fruit and Mary half the rind. Is this Pareto optimal? If not, find me a Pareto improvement. Hopefully you've noticed at this point, everyone in this example has things that they value. So this one seems pretty good. Are there other Pareto allocations? Yes. There are an infinite number of ways to slice, dice, and zest this orange such that we have no Pareto improvements possible. I would encourage you to try to find some additional ones on your own. It's kind of fun. So the reason we went through all of this work to think about Pareto optimality is because Pareto optimal is going to be our basic standard for equilibrium when we do Edgeworth box problems. Edgeworth boxes, the next thing we got to derive. So here we have sort of budget frontiers for goods for Jane and Denise. Now, suppose that Jane and Denise wake up, let's say on a desert island, and they have candy and wood. Yeah, the setup's a little weird, but we don't ask questions. It's like Lost, but slightly lamer. We're going to say that their endowments are Jane has 30 cords of firewood and 20 bars of chocolate. Denise has 60 candy bars and 20 cords of wood. What do you notice about these indifferent curves? Are they substitutes? Are they complements? Well, hopefully you notice that they're neither. These are nice, curvy indifference curves. Looks like they're kind of Cobbs-Douglasy. Next question we'll say is, let's say they've arriven at this location and they each have the items that they were given. That is, Jane has 30-20, and Denise has 20-60. What can each of them consume if they don't trade? Like, what is the set of combinations of wood and candy that Jane can consume if she doesn't trade with Denise? Well, if she doesn't trade, she can consume up to 30 cords of wood and up to 20 bars of candy. So it seems like she can consume anything that's a box. How about Denise? What can she consume? Well, hopefully you've noticed that by mirror, she can also consume this whole box. But it's weird, right? Imagine that we have this situation, and Jane really likes candy and doesn't need wood, and Denise really likes wood and doesn't like candy. Unless they engage in trade, there is no way for them to get themselves to these potentially much improved outcomes. So this is why we need to go from these two separate graphs to what is called an Edgeworth box. To make an Edgeworth box, you gotta pull what we call the Missy Elliott maneuver. We gotta take Denise's frontier and flip it and reverse it, and then staple it to Jane's. So picture the bottom left origin going up. This is Jane's possibility frontier. Jane's indifference curve and her endowment. We're just going to take Denise's and make it such that moving to the right in Jane's land increases her, but decreases Denise. And moving up increases Jane's quantity of wood, but decreases Denise's. If you do this, you can combine them to make what is called an Edgeworth box. So here I've just combined Jane and Denise's indifference curves and endowments into one single graph. As before, you'll note that Jane has 20 candy, 30 wood, and Denise has 60 candy, 20 wood. So for any point in this box, what does that point mean, right? What is point F? What is point E? Well, if you note, Jane has 20 candy, and Denise has 60 candy. In total, they have 80 candy. Similarly, Jane has 30 wood, and Denise has 20 wood. In total, they have 50 wood. So all the Edgeworth box does is says, well, how much of the 50 wood does Jane have, The rest of it must be with Denise. Similarly, how much of the candy does Jane have? Denise must have 80 minus that. So if we were to take any point in this graph, what it tells us is how we're dividing the fixed quantity of wood and candy among the two individuals. It gives us an allocation. Some additional things we should note. Edgeworth boxes are only possible if we have two individuals and two goods. If I have additional individuals, I got to turn this into a hypercube. Same thing with additional goods, right? I can't map this in 2D, and if you try to map it in additional Ds, it'll hurt your brain. Next, each axis, as we just stated, will give you the total quantity of something available. That is, the x-axis is how much wood is there in the world. The x-axis is candy, and the y-axis is how much wood is in the world. Next, you will note that Jane improves her situation by moving up and to the right. Right? As we move up, Jane gets more wood. As we move right, Jane gets more candy. Conversely, Denise gets better off by moving down and to the left. Jane gets more wood by moving down, and she gets more candy by moving left. Lastly, you'll note that although we initially had two graphs with two endowments, we now have one endowment. Point E tells me how much candy Jane has, how much wood Jane has, how much wood Denise has, and how much wood candy Denise has. So the points in this diagram are actually giving me each of the two goods for each of the two people. Pretty neat. A lot of information in these little boxes. So to remind us, Jane's indifference curve is in pink. Denise's indifference curve is in blue. Jane is made happier by going this way. Denise is made happier by going this way. And their endowment is given by E. So, looking at the endowment, how much candy does Jane have? How much wood does Jane have? How much candy does Denise have? How much wood does Denise have? As we said before, this is just given by your endowment, right? 30, 20, 30, 60. Next, let's think about the different regions in this diagram. If we start at point E, how does Denise feel about all of the points in region A? We're going to call that the green area. And how much does the other person feel about the entire green area? Next question, how does Jane feel about the blue area below the pink line? And how does Denise feel about the blue area beneath the pink line? Lastly, tell me how much each of the two individuals feels about this lens in between the two indifference curves. Answer that one out, come back to me. So you will note everything in this green region is above the pink line, therefore must be better for Jane than point E was. Conversely, since Denise's indifference curves are going to be parallel and increasing as we move to the south and west, it must be that these points here are worse for Denise than E, right? They are above her indifference curve, and her indifference curves are increasing to the down and left. So in point A, we have made Jane better off, but Denise worse off. How about places in region C, the blue region below the pink line? How do Jane and Denise feel about those? Well, by converse, if you are beneath the pink line, you have made Jane worse off. However, if you are beneath the blue line, since this increases in this direction, you've made Denise better off. Lastly, how do we feel about this lens called region B, that's in between the two indifference curves? Well, you'll note in this lens, you are above the pink indifference curve, and you are below the blue indifference curve. So this is the magical region that makes both of the two individuals better off. That is what we would say an area we could think about. There's potential for trade, right? If they're at E, if they ended up going to any other point in this lens, for instance, F looks pretty good, they're both happier. They're both better off. We also didn't talk about the white regions. Tell me how the two girls feel about these white regions. Next, with this in mind, where could I look for points that Jane and Denise both prefer to point E? Again, we just talked about this whole lens, B, that is better for both girls. So when we think about where they should trade to make both themselves better off in a util sense, we should be looking at points like F. So F is one point they both like better than E. Are there any other points? Well, sadly, there's infinite points in this lens. It's a big area, a large number of infinity of dots. So how do I figure out which one of these is best? Well, first thing we could do is let's pick some point, let's call it X. I could redraw the indifference curves for both girls. If they looked like this, is point X Pareto optimal? Or can we do better? Well, you'll note at point X, there's still this lens, right? There's still regions that are below Denise's indifference curve and above Jane's indifference curves. So if we tried pick point leaving as a region like this, we'd have to try again. We'd say, okay, well that was okay, but we can still improve. Draw again. And if we were unlucky, we still might get a lens where things could be improved. If, however, I were extremely lucky, I might pick a point such that the indifference curves for both girls going through that point don't have any lens between them. That is, they are touching exactly once at some dot inside the lens created by the initial point E. That is, we start at point E. We've just guessed, hey, let's try point F. You'll note F is inside the lens of the indifference curves, right? It's in this region. And moreover, the indifference curves at F don't overlap. What have we found mathematically regarding the indifference curves at F? Hopefully you've noticed a pattern. We found a tendency. These two indifference curves have the same slope at point F. So that means there is no lens of possible improvement. Therefore, this is our efficient outcome. This is our Pareto optimal outcome. So this is actually how you find a Pareto optimal outcome graphically. You're going to want to find a point such that the indifference curves for both individuals are tangent, and that will give it to you. If you're at this point, there's no possibility to make either Jane or Denise better off without harming the other individual. However, you will note there's a lot of points, like F, that make both girls better off and don't harm either girl. You'll note that if I move from E to any point inside this line between B and C, I will have the same phenomenon. That is, both the indifference curves will meet and be tangent at all points along this line. Moreover, if I don't care about making things fair in relation to their initial endowment, there are a lot of other points that are also quote-unquote Pareto optimal, even though they don't improve upon E for both girls. Right? I could find points all the way from A through G along this line, where the indifference curves are tangent. All of these points come together to form what is called the contract curve. To be clear, the contract curve is defined as all infinite points where if you were to draw indifference curves for both girls, they would be tangent. Therefore, the contract curve gives us all points that are Pareto optimal, i.e. all points that are efficient, i.e. all points from which the girls cannot engage in beneficial trade. There are some things that are interesting about this contract curve. First, look at point A and look at point G. Why are points A and G on the contract curve? Well, hopefully you notice that at point A, Denise has everything. Can I improve Jane's outcome if I move from A to any other point in this box? Certainly. But can I improve outcomes for Jane without hurting Denise? No. Denise has everything at A. She values everything at A. Therefore, if I move from A, I'm hurting Denise. That won't work. The converse at G. At G, Jane has everything. If I move from G to anywhere else, I can certainly help Denise, but I can't help Denise without hurting Jane. Therefore, G and A although incredibly unfair from like a equality standpoint. They're both Pareto optimal. Next, why are points like E and points like X and points like Y, why are those not on the contract curve? Why are they not along this curve through the middle? Again, at all of these points, there are other points that make at least one of the two girls better off without harming the other. Next time, we're going to start using these Edgeworth boxes to try to math out real solutions, but we'll be much better off due to our firm foundation of graphical understanding of what these boxes look like. Thanks so much. See you next time. Bye.